So in this video, I'm going to discuss a topic that's very strange sounding. It's keto-enol tautomerization. And at its core, this is really nothing more than an illustration of something from the ozone video. The idea is that a carbon-oxygen double bond is worth more than 2 carbon-oxygen single bonds. And this really drives a lot of chemistry. It's the core of organic 2 type chemistry. Anyhow, this is a very key concept. If you have a choice between a pair of carbon-oxygen single bonds and a carbon-oxygen double bond, the equilibrium will lie toward the carbon-oxygen double bond. But this is by distinct contrast to carbon-carbon double bonds. As it stands, most carbon-carbon single bonds are worth about 90 kcals per mole, details varying on what else is around there. So a pair of carbon-carbon single bonds is 180 kcals per mole, whereas a carbon-carbon double bond is 174 kcals per mole, which means that on average, it's better to have 2 carbon-carbon single bonds than it is to have a carbon-carbon double bond. It's better to have a carbon-oxygen double bond rather than 2 carbon-oxygen single bonds. Okay, so the reason why this matters is because there's a functional group called an enol, and it's so named because it's the combination of an alkene, a double bond, and an alcohol. So an enol is specifically an alcohol where it is connected, it is conjugated to the double bond. So if you have an enol, it can be converted in acid or base to the ketone form, and the equilibrium lies strongly to the right. If you have an enol, it will tautomerize and change over to making a ketone. If you have a different kind of enol, one where there is a primary alcohol, if you will, it's going to be a vinyl for primary alcohol, then equilibrium will again lie far to the right. It's just that you're going to make an aldehyde instead. So both of these are enols. The top case is a ketone, the bottom is an aldehyde. Equilibrium will lie strongly to the carbon-oxygen double bond side, and that's because of this finding right here. The mechanisms are really why I want to focus on this. In either acid or base, you can convert a enol into a ketone and back again, or an enol into an aldehyde and back again. It can go either way, and I will show you the mechanisms for enol to ketone in acid and enol to ketone in base. And from that, you can infer the other. So I invite you to work through all the mechanisms. It's a good exercise. In order for us to do a tautomerization, what needs to change is kind of a resonance idea, but not entirely, because the other thing that happens is the hydrogen that's present at this position moves to that position. Really what I need to do is draw out the implicit hydrogens so that you can see them, but the main idea is that this hydrogen ends up moving over to this position because that's the difference between the two structures. In both cases, what we have is 6 hydrogens. In the enol form, it's a movement of the hydrogen that's bound to the oxygen to a hydrogen that's bound to the carbon. That's the change. So what you need to do is pull off a proton, rearrange via resonance the charge, and then put the proton back on. And the order matters. So in acidic conditions, we can never have NO-, and under basic conditions, we can never have a O+. Because we can't do so by taking the hydrogen away from the oxygen, what has to happen is the double bond must first pick up a proton. And after an equilibrium step, we have now arrived at this structure, and you will recognize that the carbon has a plus on it, which means that the carbon is not particularly happy in this, but we do have another resonance form, and the other resonance form is simply the more stable version where the carbon now has full octets. So in the one resonance form, the carbon has a full octet, but the oxygen is plus, so that is the better of the 2 resonance forms. In the other resonance form, the carbon lacks for an octet, but the oxygen is relatively speaking content. Now, of course, this will only happen in the presence of some acid and some other solvent, so whatever the counter ion for the acid was, let's assume that this was a strong acid, so we have H+ and X-. Whatever X- or base is around will simply come by and remove the proton. So the result is 2 steps. First, you add a proton, which then leads to a charge, a positive charge on a carbon, which is stabilized by resonance, and then you remove the proton, final product, of course, being the ketone. Under basic conditions, what we're going to do is reverse the order of those 2 steps. So under basic conditions, what we have is some relatively strong base. So what has to happen first is you remove the proton first, which will now put a minus onto that oxygen. And that oxygen is reasonably content to have a minus on him, but of course, there's a better resonance form for the purposes of illustrating where this goes next, even if it's worse in in terms of its stability. So if we look at the other possible resonance form, what happens is that there's an anion at the carbon instead. Here, the more stable resonance form is the one on the left with an oxygen that has a minus on it. Everything has a full octet. Over here, everything has a full octet, but now the carbon has a minus. So this is the less preferred resonance structure, but the nice thing about this resonance structure is it shows how you make the other tautomer. What you do is simply deprotonate so that you return to the base, and what you're left with then is your final product. Under acidic or basic conditions, you can convert an enol into a ketone, and vice versa. You can simply reverse the steps. So under acidic conditions, what needs to happen is that the ene must pick up the proton first, which leads to a cation that's stabilized by resonance. Then that cation gets deprotonated. The one resonance form that reacts is the one that has an oxygen with a plus on it and a proton. So first you pick up a proton, then you pull it off. Under basic conditions, you essentially reverse the steps, and that's because under acidic conditions, the oxygens need to be neutral or plus, and under basic conditions, the oxygens need to be neutral or minus. So you deprotonate first, making the O minus, the electrons can rearrange, the carbon can then pick up proton, and that's how you convert back and forth. This is keto-enol tautomerization in a nutshell, and the reason why it matters is because if you add water to an alkyne, then you're going to make enol type species, which then tautomerize.